To send humans to another star system within a single decade, you do not build a sleek, self-contained rocket. You build a 45,000-ton, heavily layered habitat and push it down a pulsating, segmented corridor of petawatt lasers. For context, 45,000 metric tons is roughly 100 times the mass of the International Space Station. Accelerating that much mass to near the speed of light using onboard fusion or antimatter drives is mathematically unviable. The Tsiolkovsky rocket equation dictates that the propellant required to push a payload that heavy, that fast, would be exponentially more massive than the ship itself. The strict physical solution is to leave the propulsion engine behind. By drawing thrust entirely from external optical beams generated in the home star system, the spacecraft bypasses the massive weight penalty of carrying its own fuel. But while beamed power solves the mass problem, it collides immediately with the absolute limits of optics and thermodynamics. A simple, continuous laser highway stretching across light years is a physical impossibility. Overcoming the void requires a disjointed, highly engineered hybrid megastructure. The baseline ambition for a crewed interstellar transport is maintaining a continuous 1g proper acceleration. This rate mimics Earth gravity for the crew, while compressing the journey to nearby stars into a strict 10-year ship time window. This chart plots target speed against required kinetic energy. As velocity nears the speed of light, the Lorentz factor dictates an exponential energy spike. We find the viable mathematical balance point at 0.95 C. Beyond this, energy costs climb steeply, breaking the architecture's budget. Compounding this energy wall is the relativistic Doppler shift. As the ship accelerates towards 0.95 C, the incoming propulsion beam from Earth becomes severely redshifted from the spacecraft's perspective. That frequency shift drastically reduces the physical momentum transferred by each photon. To maintain a continuous 1g of thrust, the home star system must exponentially scale up its laser power output. Pushing a massive crewed ship past 0.95 C requires multi-exawatt power generation for almost zero measurable reduction in travel time. The engineering limit is firmly set. The next constraint is geometric. A common assumption is that a single powerful laser can maintain a perfectly tight focus entirely across the interstellar void. This animation illustrates the Rayleigh criterion. Over deep space distances, even a perfectly calibrated near-infrared laser will diverge into a massive cone that completely spills over a target receiver. Shortening wavelengths to X-ray reduces diffraction, but high-energy photons destroy solid materials instead of reflecting. Therefore, the strict optical solution requires segmenting the route. Over these shorter hops, 1-kilometer transmitters keep the near-infrared beam perfectly focused within the 5-kilometer sail. But a linear sequence of relays introduces a catastrophic vulnerability. If the ship drifts and misses the beam, that petawatt laser travels straight down the corridor, striking and vaporizing the unshielded downstream relay station. To prevent a chain reaction of destruction, the architecture demands an offset geometry. Relay stations must be positioned laterally, thousands of kilometers off the central axis, firing inward at the transit corridor. Diffraction physics and safety margins eliminate the possibility of a straight-line highway. The beamway must be a zigzagging chain of offset, precisely synchronized relays. Even if a civilization constructs this offset relay chain, they face the severe thermodynamic penalty of bouncing a beam thousands of times across passive mirrors. This chart plots the remaining beam power against the number of relays in the chain. Assuming a highly optimistic mirror efficiency of 99.9%, the power drops to less than 1% after passing through just 4,600 relays. At a spacing of 500 million kilometers, 4,600 relays span less than half a light year. Passive mirrors absolutely cannot carry a petawatt beam across the 4 light-year gap to our nearest neighboring stars. The system requires active intervention. The corridor must feature massive, periodic powered hubs situated in deep space. These hubs intercept the degraded beam and regenerate it from scratch using immense onboard power generation. Regenerating petawatt beams relies on heavy deuterium and helium-3 fusion. Sustaining this forces continuous industrial-scale atmospheric mining of gas giants, much like Uranus. Because deep space beam regeneration is so heavily resource-dependent, constructing a fully continuous rail between stars is entirely impractical. Ships must accelerate using a localized, near-star launch arm, cut the power, and coast through the deep void. When the beam cuts off, the 45,000-ton ship begins a decades-long coasting phase. At a fraction of the speed of light, the near vacuum of the interstellar medium transforms into a highly lethal hazard zone. At 0.95 C, striking a single millimeter-sized dust grain transfers kinetic energy equivalent to detonating tens of tons of TNT directly against the hull. Defending against this kinetic bombardment cannot be handled by the propulsion receiver. A single surface cannot simultaneously act as a flawless petawatt laser reflector, a high-capacity thermal radiator, and an armored kinetic shield. Protection requires multi-band active corridor clearing. High-intensity ultraviolet lasers fire ahead of the vessel to pre-ionize incoming microscopic dust, instantly converting solid grains into an expanding plasma state. Once the dust is ionized, the ship engages a forward Bussard magnetic sweep. This projects a massive superconducting magnetic field, sweeping the newly formed plasma harmlessly around the physical hull. Surviving the interstellar coast dictates a strictly separated layered architecture, a heavily armored forward mass shield leading the way, perfectly isolated from the delicate propulsion sail towed at the aft. Approaching the destination system introduces the architecture's final paradox, decelerating the massive ship. A reverse beam fired from the origin star cannot effectively overtake a vehicle traveling at 0.95 C. Furthermore, focusing a braking laser from Earth to perfectly strike a forward-facing receiver light years away, while entirely avoiding the ship's trailing, delicate aft infrastructure, exceeds all plausible diffraction limits. The most viable braking solution is entirely independent of optical beams. The ship deploys a colossal magnetic sail, a magsail, to create immense electromagnetic drag against the target star system. By projecting a magnetic field hundreds of kilometers wide, the magsail violently interacts with the dense interstellar medium and the destination star's outgoing solar wind, safely dragging the ship's velocity from 0.95 C down to interplanetary speeds. This yields the least impossible configuration for relativistic transit, a heavily layered habitat pushed out of its home system by a segmented offset optical launch arm, coasting across the cleared deep void and braking magnetically. An interstellar beam rail is mathematically permitted, but it demands strict obedience to the limits of optics and thermodynamics. It is not an elegant, continuous highway of light. It is a disjointed, brute force hybrid megastructure.